Okay, now let's look at problem 2, where we'll compare hydrides of different elements in terms of bonding, molecular structure, and physical properties. So in part A, we ask to identify how the covalent bonding in silicon hydride is different from the bonding in the other three hydrides. So covalent bonding can be different in two ways: polar covalent bond or non-polar covalent. So basically, we just have to identify if it is a polar covalent bond or non-polar covalent bond. So if the question states that it is different from other bonding, okay, so let's look at the other hydrides. So if we know the trend in electronegativity values in the table, so that is, it increases from bottom to top, from left to right, okay, we expect the values for oxygen, nitrogen, and chlorine to be higher than silicon, because they are located more towards top right corner, okay, so nitrogen, oxygen, chlorine, and silicon is located more towards left side, okay. So we expect the bonding between hydrogen and these elements to be a polar covalent due to the bigger difference in electronegativity values, whereas silicon will have the lowest value, and the difference between hydrogen and the silicon will be the lowest in comparison to other hydrides, okay. And in addition, we know that the hydrogen, although it is located in group 1, it has similar electronegativity value as carbon, group 4 element. And silicon is located just below carbon, therefore we expect silicon to have the similar electronegativity value as carbon. Therefore, the difference between silicons and hydrogen electronegativity values will be low, for the bond to be a non-polar covalent bond. So the bond between silicon and hydrogen is a non-polar covalent bond. Okay, whereas in other hydrides it is a polar covalent bond. Okay, in the next question we should predict the state of silicon hydride at room temperature. Okay, so the states of the compounds, that is, it is solid, liquid, or gas, depends very much on the bonding. Okay, it is intramolecular bonding or intermolecular bonding. So if we know that the bonding in silicon hydride is non-polar covalent bond, okay, and it is not an example of giant covalent structure, that means it belongs to the simple molecular structured group. Okay, so silicon hydride is a simple molecular compound. Okay, simple molecular structured compound. Okay, so if we know that it is simple molecular structure, okay, that means it is held together by intermolecular forces. So the next step is to identify what kind of intermolecular force it is held by. Okay, so for that identification, we should know the shape of the molecule. Okay, so silicon is in group 4. That means it has 4 valence electrons. Okay, and it forms four bonds with 4 hydrogens. Okay, that means it will form a tetrahedral shape. So 4 electrons from silicon, okay, and 1 from each hydrogen. Okay, so that means silicon does not have any lone pair, so it will distribute the bonding pairs evenly to form a tetrahedral shape. And if we know that the bondings are non-polar, so there is no charge distribution, the overall molecule will be a non-polar molecule due to its symmetrical shape. So the tetrahedral is a symmetrical shape. It's a symmetrical shape, and in addition to that, it is bonded to 4 identical atoms, so the molecule will be overall non-polar molecule. So it's overall a non-polar molecule. If the molecule is non-polar overall, we know that it is held together by van der Waals forces. Okay, so it is a non-polar molecule overall, non-polar molecule. Therefore, it is held together by van der Waals forces. And we know that van der Waals forces are very weak intermolecular forces, okay, making the attraction between the molecules very poor. So the molecules will be far away from each other for the state to be in gaseous state. Okay, so therefore the state will be a gaseous state. Okay, so here just one important point to emphasize, that although you after identification each bond to be a non-polar covalent bond, you should not say automatically that the molecule will be a non-polar overall. Okay, because there is examples of phosphine, for example. Yeah, the bond between phosphorus and hydrogen are also non-polar covalent bonds due to low electronegativity difference, okay, between these elements. The overall polarity of the molecule will be a polar molecule. So it will have some dipole moment. Okay, so polar molecule overall. Why? Because it has a lone pair on the phosphorus. Okay, so, and due to a negative charge of the lone pairs, okay, so it will have some polarity towards lone pair. Okay, so it's example when all the bonds are non-polar covalent bond, but the overall polarity of the molecule will be a polar molecule. Okay, so in the next question we should identify the shapes of the ammonia and borane by referring to their loose structure and valence shell electron pair repulsion theory. Okay, so let's start by first by drawing their loose structure. So ammonia, nitrogen is located in group 5. Therefore, it has 5 valence electrons. Okay, so first putting 4 electrons on each 4 corner and then pairing them up. Okay, and boron is in group 3, so it will have 3 valence electrons. Okay, and it forms 3 bonds with 3 hydrogen elements. So we know that it is a covalent bond between nitrogen and hydrogen, boron and hydrogen, therefore they will share the electron pair between each other. So they are sharing, okay? And here is similar, they are sharing electron pairs. Okay, so we can just replace this bonded electron pairs with single lines, meaning it's a covalent bond, okay? And redraw it. Okay, and now let's refer to this theory. So according to this theory, the electron pairs will place themselves in such a way to minimize repulsion between each other because they have negative charge, and we know the same charge will repel each other. Okay, so and we know that lone pair has a greater repulsion effect than the bonding pairs, so they will the lone pair will push the bonding pairs towards bottom. So the bonded pairs, okay, will be moved more towards the bottom, making the ammonia to have a trigonal pyramidal shape. So it's like a trigonal base, okay, and pyramidal. So trigonal pyramidal shape with a triangular base. Okay, and the angle between these bonds is 107 degrees. Okay, in the case of borane, there is no lone pair, so the bonded pairs will place themselves in such a way to minimize repulsion. So therefore, the shape will be a trigonal planar. So I have drawn badly, but the angle between each bond pairs is even, so 120 degrees here. Okay, so trigonal planar. Okay. So in the next question, we should suggest a reason why borane is unstable. So it does not exist as a single borane molecule and usually forms a complex with other molecules such as ammonia or as a dimer of borane, so as a B2H6 or a complex with ammonia. So ammonia will donate its lone pair to borane to form a dative covalent bond. Okay, so why is that? So if we count the valence electrons after it forms a bond, okay, for boron, So it has so 1, 2, 3, 4, 5, 6. So it has 6 valence electrons. So boron has 6 valence electrons in BH3 molecule, okay, in boron molecule. So you see, it is not a stable octet state, okay. So it is lower than 8 electron. So it is an electron deficient compound, okay. It's an electron deficient molecule. Therefore, it will be willing to form other bond, okay, to form other bond by so therefore gaining more 2 electrons to obtain 8 electron state, okay. Okay, in addition to that, the small size of hydrogen allows for the molecule to form complex. For the molecule to form a complex. Why I am saying that? Because boron trichloride, okay, also although boron trichloride has also 6 electrons, which makes it an electron deficient compound, it does not form a complex. So it exists as a boron trichloride. Okay, so why is that? Because the big size of chlorines does not allow the other molecules to approach the boron trichloride molecule and form a complex. Okay, so chlorine molecules has big sizes. Okay, so other molecules cannot approach it, whereas hydrogen has small size, and boron can form a complex with other molecules. Okay, now in the next question we should compare the boiling points of ammonia and water. So water has much higher boiling point than ammonia. Okay, so why is that? So the bonding, the intramolecular bonding in both molecules are polar non-covalent, polar covalent bonding. And they both are simple molecular. They both are simple molecular structure compounds. Okay. That means they are held together by weak intermolecular forces. Okay, so both simple molecular. So furthermore, so what kind of intermolecular forces? So hydrogen is bonded to a high electronegative atom, which is nitrogen, oxygen. Okay, therefore they will form hydrogen bonding. So we see that they both have similar characteristics and similar intermolecular forces. Why is that then water has much higher boiling point? Okay, it is explained by the numbers of lone pair and the hydrogens in each case. So let's compare the numbers of lone pair and hydrogen in each case. So in ammonia has 1 lone pair and 3 hydrogens. Okay. In the case of water has oxygen has 2 lone pair. Okay, and 2 bonds with hydrogen. Okay. So in the ammonia case, ammonia cannot use. So although it has 1 lone pair and 3 hydrogens, so in overall 4 ways for ammonia to form a hydrogen bond. For water as well, yeah. So 2 lone pair and 2 hydrogens, so making it for the water molecule to form 4 hydrogen bonds. Okay. However, in ammonia, there's only 1 lone pair and 3 hydrogens. So it cannot form hydrogen bonds efficiently. So it cannot use its all 3 hydrogen efficiently. So it kind of 2 hydrogens will be wasted. Okay. In the case of water, it has well balanced number of lone pair. So 2 lone pairs. Okay, and 2 hydrogens. So it will use these chances. Okay. So 2 hydrogen, 2 lone pairs to form hydrogen bond efficiently. Okay, so there is more chance for the water molecule to form more hydrogen bonds than ammonia. Therefore, the water will has much higher boiling point.